Hi everyone. So what I'm going to try to do is mimic how we would usually do some of the sample problems in class. So already uploaded on EC Learn is a Word document with all of the problems that we're going to do. This first video will be for sections 9.1 through 9.3, and then we'll do another video for 9.4 through 9.6. So why don't we get started? So the first question is asking us in each of these to identify the solute compared to the solvent. So if we take a look at the first one we have a binary solution. It's going to be made out of sugar and water. And then all we need to do is remember our definition for what a solute is and what a solvent is. Because to make a solution, you're going to need a mixture of both. Other than that, it's just a pure compound. So we need to remember that solute is the minute component, or the small component, right? And then solvent, I don't really have a moniker or mnemonic device or whatever it's called to remember that, but there's only a choice of two. So if you know that solute is the minute component, I think I got a better stylus. I can try doing print again. Seems like that might be a better alternative then, but I'll still have to go back to cursive if things aren't working out. But yeah, we already discussed that in the video. So we have our solute as the minute component. Take a look here, 2 grams of sugar versus 100 milliliters of water. This is something we're getting familiar with, but the density of water we know is always 1 gram per 1 milliliter. So if I got 100 mils, I know I have 100 grams. So in the case A, sugar is going to be our solute. Why? Because it's in a smaller amount than the water. We take a look at part B. Both of these are liquids. The first one is ethyl alcohol, the second one being methyl alcohol. And we're given their amounts, 60 mils and 30 mils. So by our last definition, we're looking for the solute, which is the minute, or the small part of the solution. The small part is going to be methyl alcohol. So a pretty straightforward attack to those types of problems. And there's our answers we just arrived at. And so study check part 2. Sorry every once in a while to see that flash. That's when my stylus is kicking in. So we're still in 9.1, but our second study check question. So it's giving us a solid, lithium chloride, being added to water. And then it's asking when this molecule, lithium chloride, dissociates into anions, right? Because as it's dissolved into water, soluble ionic compounds separate into a cation, into an anion, but they're not just floating free in space, right? We need to find out what the lithium ions are going to be attracted to. So we know opposites attract. So actually the lithium plus will be attracted to water molecule, the oxygen in the water molecules. So if I sketch that, right, there's my lithium cation, and if I have a molecule of water, water is polar. One part of the molecule is partially positive, the other is partially negative. Opposites attract. And then we can use the same logic for here. The chloride ions in the water from the lithium chloride will be attracted to, in this case, the partial positive hydrogen. How do I know that? Again, I can sketch that. There's my Cl minus. And when I draw my molecule of water, still polar, because that oxygen is pulling electron density towards itself, so the partial positive will be interacting with the full negative on the chlorine. And so it's exactly what we see here in the solution slide. So the next one we have, this is our third one from section 9.1. So it's asking which of the following solutes will dissolve in water, and then to ask us why. So the first thing we want to remember is like dissolves like. Water, we already know, is polar. And if we forgot, we can draw the structure of water. Oxygen is going to be very electronegative. It pulls the electron density up, so it's definitely going to be polar. So that means polar solutes will dissolve in water. So we take a look. Right off the bat, I can say we can probably get rid of one of these, because if I look here, let me try to change colors. Come on. And it's not letting me. Let me do it this one. There we go. We can already cross off gasoline because it says it's non-polar, and we're looking for polar solutes. I2 we can dump right off as well, because symmetrical molecules, especially when they're made out of the same atom, because they're equal electronegativity, equal pull, there's no dipole, I2 won't dissolve in water. So what that's going to leave us with, and this is going to erase all my strokes, but we'll go back. So no gas, no I2. That leaves us to determine if either of these last two would be soluble in water. So sodium sulfate, that's an ionic solid. We don't, for this class, delve deep into what compounds will be soluble and what won't be when they're ionic. Just know that some are soluble, some are not. This one is going to be soluble, so that will definitely dissolve in water. And then HCl. This is a little bit simpler. We don't need to know exactly if it's soluble or not in water. We can ask the question, is it polar? Well, if we draw out our dot structure, we'll find out chlorine is very electronegative. It's going to pull electron density towards itself, and again, resulting in a polar molecule. So HCl, that's actually hydrochloric acid. Hydrochloric acid, which is definitely soluble in water. So A and D would be our answers. That's exactly what we see. So 9.2, electrolytes and non-electrolytes. So the first question we're asked is a two-part question, and it says, complete each reaction for the strong electrolytes in water. So first thing that draws my attention should be the word or phrase strong electrolyte. So strong electrolytes, we only have one definition. They fully dissociate in water. So that means this compound, CaCl2, here, we need to write it in such a way that it is dissolving fully. And for us, we'll take 2 seconds. You can pause the video, it's a little bit easier, and then decide which one, A, B, or C, will complete our reaction. And for me, well, not for me, the correct answer is going to be C, right? There's a reason we're not choosing B. Oh, sorry if you can, oh, I'm just getting emails. The reason why B is going to be incorrect, it did dissociate. I have my cation here, but this, right, the chloride 2 minus, this is not the anion that's actually going to form. And how do I know that? Well, I know from the structure of calcium chloride. Because if I do out the dot structures, calcium was donating 2 electrons, each chlorine was donating 7. And so we can see it's going to be kind of weird, but we could make bonds like that in which each chloride are they're separate from each other. So when they do dissociate, I got my calcium, let me fix that. I have my calcium 2 plus cation, and then 2 individual chlorines, so I could write that like this. So that was a lot of writing, a lot of talking, hopefully for something that's pretty straightforward, because we can apply the same logic to question number 2. So we have our potassium phosphate. And again, what we need to pay attention to is going to be, what is this going to dissociate into? So I have KPO4. I would recognize that potassium, all right, it's found in group 1 of the periodic table, which we know will have a +1 charge. Phosphate, right, that is one of the polyatomic anions I had you memorize. So phosphate. So those are going to be our individual parts. So I got 1 phosphate, I can see that here, and 3 potassium. And what does that look like? A, right here. 3 potassium and 1 phosphate. And it's exactly what we see. C and A were our correct answers. So again, we'll do a little bit more practice. Right. So which of the following reactions represents the dissociation of a strong electrolyte in water? So the best way to go about this would just be going by systematically. So I take it, look at number 1, and I have ammonia, and it's forming a complex with water. So this is not dissociating, it's actually forming a new molecule. So I'm going to say for now, not strong, or maybe I don't know, right? So we can keep going through. You take a look at the next one. We have this compound here. I can tell because I can look at the structure. I know it's methanol. Nothing's happening here except a change in state. So there's no dissociation, so it cannot be a strong electrolyte by definition. So we easily got rid of that one. We take a look at letter C. So we have our sodium sulfate. We see that the sodium fully comes off as at 2 Na pluses, and then I have my polyatomic ion sulfate. This one, it will definitely be a strong electrolyte because it's ionic. Oh, I can't spell electrolyte, but you know what I'm writing. I'll call it elec. So we can see it's ionic, and then when it's added to water, it breaks up into individual ions, be it something like Na plus or polyatomic ion. Then we take a look at our last one. Here I can tell this by the structure, I know the name, it's ethanol. Again, just like with the methanol example, we see all it's doing is changing state. It is not dissociating. We know that's right off the bat can't be true. Now let's take a look at our answer slide, because we only have a choice between A and C. If I was going to use deductive reasoning, C seems to be the right choice. And it's exactly what we see. Oh, I just lost my dossary. Hold on one second. Gotta get my pen back. Alright, there it goes. Almost. Go back a few slides. Alright. Now it's asking us to write the equation for the formation of a solution for each of the following. So the dissociation, so we're going to pick up on key words. We're seeing dissociation and strong electrolyte right off the bat. So we have a strong electrolyte, this K2CrO4, so potassium chromate, dissolving in water. So we always write with what we're starting with. So there's my potassium. Oops, why did I put phosphate? Or started to write phosphate. Potassium chromate. Solid. It's dissociating into water. So we'll write it as going across the top of the arrow. And then what we can do is balance the equation and then make sure we write the correct ions. And with the correct state of matter. So we have our 2 potassium plus aqueous, so it's a little messy with the stylus, and then we have our chromate 2 minus aqueous. So now we're looking at part B. So we're looking at partial dissociation. Right off the bat, that's going to be telling me I'm going to be looking at these back and forth arrows instead of the unidirectional arrow we see in part A. So we have a partial dissociation of the weak electrolyte phosphoric acid, and it's going into water. So again, we write with what we started. So we have our H3PO4 aqueous. It's in water. And so in this case, we'll see it partially dissociates. Let's write just losing one of those hydrogens. There's my hydrogen phosphate, and then my H plus cation. And so it would be all set there. And then the last one is saying we have a solid of sugar. It's dissolving in water. I have no other indication if it's a strong electrolyte. So I'm going to make the reasonable assumption that it dissolves in water, but it's not strong. So I will start with what I'm given. There's my sugar. It's dissolving into water, which means it will change the state of matter to aqueous. Remember, just because it looks like the solution, everything's a liquid, right? It's the liquid sugar is very hot, right? If you've ever made some kind of candy at home, but when sugar dissolves into water, it is not melting; it is just being aquated. So just keep that in mind too. All right, so this will be the last section of study check walkthroughs here. Then you guys can pick up when you want to take a break or come back or do the whole thing. I'll pick up with the final 3 sections after this. All right. So, label each of the following solutions as saturated or unsaturated. So we're actually not given any numbers, we're just given a description. It's telling me that the salt disappears when put into water. Well, if it's dissolving more, that means it can't be unsaturated. Sorry, it can't be saturated because you can put more in. It has to be unsaturated. It'll keep continuously dissolving salt until you reach saturation. Part B, sugar is added to a cup of water and does not disappear. It sits at the bottom of the cup. That is telling me that's a definition of what a saturated solution is. Why? The water can no longer hold any more sugar. So even if you add more sugar, it literally will sink to the bottom and do nothing. And that's what we see here in the solution slide. So again, we're talking about this solution, but we're not using a lot of numbers right now. We're going to get a lot of numbers in the next section. So let's rationalize, why could a bottle of a carbonated drink possibly burst or explode when left out in the sun? Well, if we think about pressure's relationship with temperature, we've seen this curve. Maybe not necessarily paid all that much attention to it, because the way we kind of left it was pretty simple. We were just saying when we're talking about what affects solubility, so temperature effects on solubility, we know that as temperature goes up, right, the solubility of a gas is actually going to go down when we're dealing with liquids. Or sorry, not liquids, when we're dealing with gases dissolved into solution. So gas dissolved in solution. So why is that the case? Well, the pressure of the gas actually is increasing, and so it's actually going to force itself out of solution. So if we draw that as a quick sketch, right, I'm just going to use a box. It will be our carbonated bottle, whatever it is. Right, we have a solution. There's some dissolved gas in here. There's a little bit up here too, but right, it's under pressure. So if I start to heat it up, I'll pretend flames down there, what's going to end up happening is these CO2s will be driven out of solution as that solution heats up, and there'll be more and more gas. And we learned in chapter 8, more gas, more pressure means possibility of exploding. And then why do fish die in water that is too warm? Again, we're going to ask the question of temperature's effect on solubility. We just described again, this is going to be the same explanation. As T goes up, right, we saw that the solubilities of gases in solution goes down. Well, fish don't, they got to breathe something, and they actually breathe the same thing we do, which is dissolved oxygen gas. And so if we heat up the temperature of the water that the fishes live in, right, I can't draw fish, whatever they look like. There we go. Oh, you guys can use your imagination, right? We have our fish floating around, but if we start to heat things up, because things are getting too hot, the dissolved oxygen will heat up and then leave the solution, killing the fish. They have nothing to breathe. So again, different explanations, but rely on the same theory. And this is exactly what we just said here. And that ends our first half of doing the study checks for chapter 9. This is going to be kind of experimental to see what works best for the class, so we'll stick with this for a little bit, and then we'll reevaluate somewhere in the middle of the week. All right.